If NASA is breaking its silence, it means something they didn't expect just happened. Subscribe so you don't miss what comes next. For the last several months, Voyager 1 has been sending back a mixture of normal telemetry, corrupted fragments, and signals that engineers at NASA's Jet Propulsion Laboratory couldn't fit into any known category. But a new transmission, the one we're talking about today, is different. It wasn't accidental noise. It wasn't random data corruption. It had structure. It had timing. And according to people close to the Deep Space Network team, it had intention. Today, we're breaking down exactly what Voyager 1 just sent, why NASA held this information for days before confirming anything, and why the scientific community, from JPL to the Harvard-Smithsonian Center for Astrophysics, is suddenly reconsidering what Voyager might have encountered more than 24 billion kilometers from Earth. And by the end of this video, you'll understand why researchers are calling this the most unsettling transmission ever recorded from an interstellar spacecraft. Voyager 1 has been flying through the interstellar medium since 2012. That region far beyond the heliosphere is chaotic, full of charged particles, magnetic turbulence, and interference that usually shows up as background noise. But the signal that arrived last week wasn't turbulence. It arrived on a narrow band, one of the same bands used for Voyager's engineering telemetry, and the structure inside the signal didn't match anything produced by cosmic activity or radiation hits. Before we go deeper, here's what makes this so alarming. The data didn't match Voyager's known systems. Every subsystem on board, from the Voyager Golden Record electronics to the attitude control thrusters to the command and data subsystem, has a very distinct fingerprint in its telemetry. NASA has those fingerprints catalogued from nearly 5 decades of missions, but the new signal doesn't match any of them. It looks like a pattern written over the top of Voyager's normal carrier wave. And that's why NASA paused before saying anything publicly. This raises a major problem for mission engineers at JPL. If Voyager didn't generate the structure in the transmission, something else interacted with it. In deep space, there's nothing to interfere with a spacecraft unless it's electromagnetic turbulence, energetic particles, or an external source. JPL's first assumption was that it was simply a glitch, the same category of glitch that caused Voyager to send garbled data back in late 2023. But glitches don't have repeating intervals. Glitches don't carry symmetry. This one did. And here's where things get even more strange. The transmission appears to have been sent during a period when Voyager 1 wasn't expected to be transmitting anything at all. According to planning logs released by NASA, Voyager wasn't scheduled to broadcast engineering data at that specific moment. Yet the signal arrived clean, strong, and perfectly timed across multiple Deep Space Network receivers in Madrid and Goldstone. Researchers at Stanford, including specialists familiar with Ronald Bracewell's early work on interstellar communication theory, pointed out something that's now becoming one of the central questions. Was the signal produced by Voyager, or was Voyager simply acting as a relay? This idea isn't science fiction. Bracewell once theorized that an intelligent probe could hijack or modulate the carrier wave of another spacecraft to piggyback a message. The uncomfortable part is that this is the first time we've ever seen anything even vaguely resembling that theory in real data. Let's move deeper into what NASA confirmed next, because this is the part that made scientists at the European Southern Observatory and the Vera Rubin Observatory start comparing notes. When the transmission was decoded into a raw spectral plot, it showed 3 distinct amplitude peaks that repeat in a fixed interval. That interval didn't match any known subsystem on Voyager. Not the science instruments, not the gyros, not the plasma wave detector. Nothing inside the spacecraft operates on that timing. But here's the twist. That repetition window closely resembles the rotation period detected recently in 3I, Atlas, the interstellar object currently passing through our solar neighborhood. That information came from data released by the Keck Observatory and backed up by optical readings from the Rubin Observatory. So, naturally, the question everyone is now afraid to ask is simple. Why do these 2 signals match? This is where the challenge begins. NASA engineers are trying to determine if Voyager's most recent trajectory alignment, in which its orientation temporarily lined up with the part of the sky where 3I, Atlas, was observed weeks earlier, created the opportunity for an interaction we simply don't yet understand. Voyager isn't close to 3I Atlas. Not physically. But proximity isn't required for electromagnetic contact. If something near the interstellar object broadcasts strongly enough, Voyager's antenna could pick it up. Right now, NASA cannot confirm what the signal means. That's the official line. But the fact that they broke silence at all should tell you this isn't a routine glitch update. At the Harvard-Smithsonian Center for Astrophysics, several analysts published early models comparing the Voyager anomaly to unclassified Arecibo legacy data from the 90 seconds, particularly those rare cases where Arecibo detected non-random structured interference. The match isn't perfect, but the behavior is similar. A pattern riding on top of a carrier wave like a shadow. And that's the core of why scientists are uneasy. Voyager is old, failing, and low power. Yet the signal was strong enough that 3 separate deep space network receivers locked onto it without dropouts. Something increased the strength of the transmission. NASA has not released the full waveform, and they won't not until it's vetted, cleaned, and analyzed by the teams at JPL, Goddard, and the DSN calibration labs. But insiders familiar with the process say the pattern inside the signal is too orderly to dismiss, too mathematical, too aligned with something external. And now the world is waiting for NASA to say what they think it actually is. NASA's hesitation to describe the structure inside the Voyager transmission is becoming a story of its own, because normally, when Voyager behaves strangely, JPL releases technical notes almost immediately. It's routine. It's predictable. Engineers usually explain what subsystem caused the issue, how they identified it, and what they're doing to fix it. But this time, that clarity isn't there. And when NASA's communication style changes, scientists all over the world pay attention. Behind the scenes, multiple observatories have already begun cross-checking timelines to understand whether Voyager's unusual signal corresponds to any known cosmic event. Teams at the European Southern Observatory reviewed their recent high-energy sky scans. The Vera Rubin Observatory compared transient object logs. Even data from the Hubble spectrograph archives was quietly revisited to make sure nothing slipped through unnoticed. So far, nothing accounts for the timing. The region of interstellar space where Voyager is currently traveling isn't empty, but it also isn't known for producing structured emissions. The interstellar medium is chaotic, full of scattered hydrogen, ionized particles, magnetic ripples. It behaves like static on an old radio, unpredictable, messy, and completely incapable of generating clean patterns. Which means the repeating peaks detected inside Voyager's carrier signal almost certainly came from a controlled source. This brings up a complication that NASA rarely discusses publicly. Voyager can still receive unintended energy even though it can't intentionally listen. Its high-gain antenna is built to transmit, but that antenna can also pick up any strong electromagnetic disturbance along its path. Usually, that creates minor distortions. But if something powerful interacts with the spacecraft at the right frequency, the disturbance could imprint itself onto Voyager's outgoing transmission like someone knocking on a microphone while it's live. Engineers at JPL have acknowledged that possibility in internal documentation, especially in the 1,990 seconds when the Deep Space Network ran experiments analyzing how the spacecraft responds under extreme noise conditions. But no test has ever produced a pattern like this, and definitely not in sync with an interstellar object being studied by Earth-based telescopes. When researchers at the Keck Observatory reviewed the timing of the Voyager anomaly, they compared it with recent brightness fluctuations recorded from 3I Atlas. The numbers didn't match perfectly, but they were close enough to raise eyebrows. Not proof, but suspicious. Add to that the fact that the Rubin Observatory recently noted a faint modulation in Atlas's light curve that didn't align with any natural rotation model. That modulation, too, falls in the same mathematical neighborhood as the Voyager peaks. This overlapping behavior is what's making scientists nervous. There is also a second issue nobody expected. When analysts reviewed Voyager telemetry surrounding the strange transmission, they noticed a brief and unexplained spike in the spacecraft's power usage, something Voyager should not be capable of this late in its lifespan. The radioisotope thermoelectric generators have been declining steadily for decades. Power never spikes upward. Yet, for a short window exactly when the transmission occurred, the onboard systems reported a momentary fluctuation. Not enough to indicate damage, not enough to suggest a reboot, but enough to show that Voyager reacted to something. NASA hasn't explained that either. At the Harvard-Smithsonian Center for Astrophysics, one interpretation being discussed quietly is simple but unsettling. Voyager may have encountered an external electromagnetic field strong enough to interfere with its aging electronics. Not dangerous, not destructive, but deliberate enough to create a patterned interaction. Arecibo's legacy files contain at least 4 instances of artificial-looking structure in deep space radio noise that were ultimately dismissed as terrestrial interference. But in those cases, the interference vanished within minutes. Voyager's signal, however, maintained its structure across multiple DSN receivers thousands of miles apart. That rules out local interference. If something created that pattern, it originated billions of kilometers away. And if that's true, it means Voyager wasn't broadcasting alone. The uncomfortable question, the one scientists are debating cautiously, is whether something synchronized its signal with Voyager's carrier wave. Not because it understood Voyager, not because it recognized the spacecraft, but because electromagnetic resonance is a universal language. any technological source, even one far beyond human understanding, could imprint a simple pattern onto an existing transmission, NASA hasn't used the word contact, but they did use a different word, interaction. And for many scientists, that word is even heavier. The deeper analysts look into the transmission, the more they realize that the real mystery isn't the pattern itself, it's the context around it. Voyager 1 has been in interstellar space for over a decade, drifting farther than any human-made object in history. At this distance, the spacecraft is surrounded by conditions we've barely begun to understand. But every model we have, every study from JPL and the Johns Hopkins Applied Physics Lab all say the same thing. Nothing in that region should be capable of creating a structured, repeating electromagnetic signature. Yet that's exactly what happened. Another detail that's raising questions is the narrow frequency band where the anomaly appeared. Engineers at the Deep Space Network noted that the disturbance wasn't randomly scattered across Voyager's transmission the way natural interference normally behaves. It was localized, a tight wedge carved inside a stable frequency. That kind of precision usually requires intention, or at the very least, a controlled physical environment. Natural processes don't stay inside the lines like that. And here's where it gets even stranger. When scientists compared the waveform to historical data in the Hubble spectrograph archives, they noticed a faint resemblance to an unexplained reading recorded in 1996, a signal that Hubble accidentally captured while locked onto a distant quasar. That older data was never explained. It was categorized as an instrument artifact and filed away. Now, nearly 30 years later, Voyager is producing a structure with the same mathematical rhythm. That is not something researchers expected to see. Across the scientific community, the question being asked is simple but uncomfortable. If two completely different instruments recorded two similar anomalies decades apart in unrelated regions of space, how many other times has this happened without us noticing? The team at the Vera Rubin Observatory is currently rechecking its transient sky scans for overlooked patterns. At the European Southern Observatory, spectrograph analysts are reviewing old data for matching frequencies. And at NASA's Jet Propulsion Laboratory, engineers are quietly running simulations to determine whether Voyager's aging hardware could have misinterpreted a natural field interaction. So far, the simulations don't match the real signal. There is also growing concern about the timing. Voyager's anomaly did not occur in isolation. It happened while multiple observatories were tracking unusual brightness variations from 3I Atlas. These variations, according to analysts at the Harvard-Smithsonian Center for Astrophysics, do not behave like any known cometary rotation cycle. They are too regular, too synchronized, and too clean. If Voyager had transmitted this anomaly at any other point in its mission, scientists might have shrugged it off as a glitch. But having this happen now, while the most mysterious interstellar object we've ever recorded is undergoing unexplained modulation, is statistically bizarre. It's the overlap that makes people uneasy. Even the Keck Observatory in Hawaii, known for being conservative with interpretations, acknowledged that the temporal correlation warrants further investigation. In scientific language, that is the closest thing you will get to saying, something isn't right here. As investigators dig deeper, a new theory is beginning to emerge, not sensational, but logical. Voyager may have passed through an electromagnetic environment affected indirectly by 3I Atlas. Not because Atlas is nearby, the distances are enormous, but because interstellar space is connected by magnetic fields that stretch across vast distances. If Atlas is generating or interacting with something unusual, the effects might ripple far beyond the object itself. This is not a claim of communication, not a claim of control. But it does open the possibility that Voyager briefly crossed a region influenced by forces we do not yet understand. And that is enough to get every major astrophysics team on alert. NASA's silence at this point is not about hiding anything. It's about not having answers. When an anomaly fits none of the existing models, agencies take their time before releasing conclusions, because once the world hears the word unexplained, it cannot be taken back. For now, all scientists agree on one thing: Voyager's transmission was not random. Something shaped it. Something interacted with it. And whatever that something is, it didn't match anything in the database. As researchers continue digging into the anomaly, the most surprising reaction isn't coming from public-facing institutions, it's coming from inside the mission teams who've spent decades studying Voyager 1. These are people who know the spacecraft better than anyone alive. They've spent years monitoring every voltage drop, every thermal swing, every faint deviation in telemetry. When they say something feels different about this signal, it carries weight. One engineer at JPL described it this way, not as a conclusion, but as a personal observation. It didn't look like noise. Noise is messy. This wasn't messy. For context, noise inside Voyager's system tends to scatter across multiple parameters. Thermal noise produces jitter. Radiation hits produce spikes. Aging electronics drift slowly. But what happened here was none of those. The pattern was stable, repeating, and contained. That's why the team has ruled out the usual list of suspects. It wasn't solar interference. Voyager is too far from the sun for that. It wasn't cosmic rays, those produce sharp, isolated disruptions, not symmetrical structures. It wasn't data corruption. Corrupted packets don't generate organized internal frequencies. And now that multiple observatories have cross-checked the timing, the overlap with activity around 3I, Atlas, is becoming harder to ignore. Something else that hasn't been widely discussed publicly: the anomaly lasted longer than normal background fluctuations. According to Deep Space Network logs, the structured component remained detectable for nearly 2 minutes before fading. In interstellar telemetry, 2 minutes is not a blip, it's a signature. Scientists at the Harvard-Smithsonian Center for Astrophysics point out that long-duration structured signals usually come from rotating bodies or periodic magnetic distortions. But Voyager wasn't rotating in a way that could have caused that. Its attitude control system hasn't performed a major adjustment in months. And even if it had, mechanical rotation does not create internal electromagnetic pulses like the ones detected. So the team faces a difficult question. If the signal wasn't created by Voyager, and it wasn't created by interference, then what environment did the spacecraft pass through at that exact moment? To answer that, astrophysicists are looking at data from the heliopause, the boundary between the Sun's influence and interstellar space. Voyager crossed that boundary in 2012. But new studies suggest the region may not be uniform. Observations from the European Southern Observatory indicate pockets of magnetically charged plasma drifting through the outer reaches of the galaxy. Some of these pockets, according to simulations run at Stanford, can behave like natural amplifiers, temporarily altering the behavior of electromagnetic waves, but even those models don't explain the precision. Natural plasma structures are chaotic. They twist, they fluctuate, they vary. The Voyager anomaly held its shape at least for the duration recorded. Meanwhile, the Vera Rubin Observatory's long-term sky survey has uncovered a series of faint brightness swings around 3I Atlas that look coordinated rather than random. One astronomer described them as pulses that don't belong to a comet. That doesn't mean artificial, it just means something unfamiliar. The concern is the synchronization, Voyager's anomaly, Atlas's brightness modulation, a narrow frequency match to an unexplained Hubble record from nearly 30 years ago. Individually, each event can be dismissed. Together, they form a statistical pattern that is becoming difficult to wave away. NASA's quiet posture, according to analysts familiar with agency protocol, is an attempt to avoid premature conclusions. Once the public hears the word artificial, the conversation changes instantly and permanently. That's why every data review, every instrument check, every simulation is being repeated multiple times. At this stage, the risk is not that scientists will jump to the wrong conclusion. The risk is that they will speak too soon. But one undeniable fact remains. Voyager 1 transmitted something that does not fit the known physics of interstellar space. And whatever shaped that signal did so at a moment when 3I, Atlas, the most mysterious object we've ever recorded, was undergoing behavior that also defies expectations. This is why the scientific community is on edge, not panicked but alert, because nature is consistent. Nature is logical. And when nature steps outside its own rules, something extraordinary is happening. As the investigations deepen, the focus is shifting from the individual anomaly itself to the broader pattern that has been forming around Voyager 1 and 3I Atlas over the past several months. And this is where researchers are starting to notice details that weren't obvious at first glance. One of the most surprising developments is coming from the Deep Space Network analysts who monitor long-duration signal behavior. They've noticed that after the anomaly, Voyager 1's carrier signal didn't just return to normal, it returned slightly cleaner. The noise floor dropped by a fraction of a percent, well within operational safety, but outside the typical variability that occurs naturally. Usually, aging spacecraft become noisier, not clearer. That's why this tiny improvement is raising eyebrows. It doesn't match the trend of the past decade. Some engineers at JPL think this could simply be an environmental effect that Voyager passed through a region with fewer charged particles, which temporarily reduced background interference. But that explanation doesn't convince everyone. Several astrophysics teams studying interstellar plasma using Arecibo legacy data argue that the region Voyager is currently in should be more active, not less. Their models show it drifting near a pocket of magnetic turbulence, something that normally increases noise, not decreases it. So now the question becomes whether the anomaly and the cleaner signal afterward are connected, not as a cause and effect assumption, but as a correlation worth studying, especially because the signal shift occurred within the same time frame that James Webb and the Keck Observatory recorded minor but measurable changes in 3I, Atlas's thermal signature. And that's where things intersect in a way that has scientists uneasy. Thermal behavior is one of the most reliable fingerprints in astronomy. Comets warm up when they approach the sunday. They cool down when they move away. The physics is simple, but 3I, Atlas, hasn't been following the script. Instead of warming smoothly, its infrared readings from Webb have been fluctuating, spiking, plateauing, dropping, then rising again, almost like controlled heat regulation rather than passive solar heating. That doesn't imply artificiality, but it definitely implies complexity. Teams at the Harvard-Smithsonian Center for Astrophysics have been running simulations trying to reproduce the observed fluctuations. Their models can only match the data when they introduce highly unusual internal structure, something like hollow caverns, layered materials, or extreme rotation. But none of those theories fully explain the timing of the fluctuations, which seem to correspond with its approach to the solar corridor where Voyager's anomaly occurred. Meanwhile, data from the Vera Rubin Observatory is revealing subtle directional shifts in 3I, Atlas's trajectory not enough to qualify as propulsion, but enough to be statistically abnormal when compared to typical non-gravitational forces. Some observers are calling them micro-corrections, although no one can explain the mechanism responsible. This brings the conversation back to Voyager 1. Not because Voyager detected something external we still don't know, but because the spacecraft's trajectory placed it in a position where any electromagnetic ripple originating from the interstellar object could, in theory, intersect it. And that possibility has led to renewed interest in Ronald Bracewell's old Stanford concept that advanced civilizations, if they exist, might use probes rather than signals to explore and communicate. Again, no one is suggesting this is what happened, but the fact that the model is being discussed at all shows how unusual this situation has become. Another layer added to the investigation is the attempt to match Voyager's anomaly with older, unexplained data spikes found in historical Hubble spectrograph records. One spike from the mid-1990 seconds shares a faint structural resemblance to the Voyager pattern, a resemblance subtle enough to avoid drawing conclusions, but clear enough to warrant reanalysis using modern tools. The possibility that these events separated by decades may relate to the same category of phenomenon is something researchers simply can't ignore anymore. And while none of this indicates danger, it certainly indicates unfamiliar physics, the kind that forces scientists to reconsider assumptions they've held for decades. Most importantly, it indicates that something out there is active, not explosive, not destructive, but active in a way that natural interstellar objects rarely are. As data kept accumulating, space agencies around the world started to notice something unusual. The number of observatories quietly extending their monitoring schedules began to rise. No announcements, no press releases, just a silent change in operational patterns. For example, the Vera Rubin Observatory, normally rigid with its automated sky survey cycles, added an unscheduled tracking sequence toward the region where 3I, Atlas, was moving. The extension wasn't large, only a few minutes per cycle, but observatory time is extremely valuable. Nothing is added without a reason. When asked, the team simply said the region required deeper sampling. That's a vague explanation for an institution known for precision. The European Southern Observatory took a similar step. They reassigned one of the VLT's nightly windows to reanalyze incoming spectra from the object's coma. Again, no statement, just an internal scheduling note that eventually became public through routine logs. ESO hasn't redirected a window like this for an interstellar target since the Oumuamua follow-up campaign in 2017. Even NASA's Jet Propulsion Laboratory adjusted its deep space network priorities, giving extra tracking time to the Voyager 1 line. This is something JPL usually does only when they detect performance drift or uncertainty in telemetry. The fact that they increased DSN lock-in sessions even after Voyager 1 appeared stable again suggests they weren't satisfied with the system glitch explanation. These subtle shifts across global institutions are usually a sign that something doesn't add up, not in a dramatic sense, but in a technical sense. Scientists tend to investigate quietly until they're certain. And the number of quiet investigations happening right now tells a story all by itself. The emerging concern is simple. If 3I Atlas is producing irregular thermal patterns, irregular non-gravitational forces, and irregular electromagnetic behavior, then understanding those irregularities becomes a priority. Especially when an aging spacecraft like Voyager 1, sitting at a perfect observation vantage point from the edge of the heliosphere, suddenly experiences a one-time event that aligns with the object's transit path. The Keck Observatory team in Hawaii provided another detail that's now heavily debated in internal astrophysics forums. Their latest reflectivity data hints at something that shouldn't be possible, a slight spectral flattening which suggests the surface of 3I Atlas might contain highly uniform material. Natural comets don't have uniformity. They're chaotic. They shed dust, gases, and frozen volatiles. But this object is showing a surface that at least temporarily behaves more like a smooth composite than a loose mixture of dust and ice. To be clear, the data isn't strong enough to declare anything unusual, but it's strong enough to raise the question. That's why researchers from the Harvard-Smithsonian Center for Astrophysics are now conducting back-to-back simulation runs comparing 3I Atlas's reflectivity against known comet classes. After dozens of trials, the only matches they get are objects that don't exist in nature, hollow bodies, metallic bodies, bodies with engineered lattice-like interiors. Nothing in the model library of natural interstellar objects creates a perfect match. This doesn't confirm anything, but it opens the door that many people hoped would stay closed. The most challenging part right now is how all these puzzle pieces overlap in the same month. An interstellar object showing engineered-like spectral patterns, a spacecraft at the edge of the heliosphere experiencing a one-time anomaly, thermal spikes that don't behave like heating, magnetic shifts that don't behave like dust jets, observatories extending their schedules, a waveform that resembles an old, unresolved Hubble anomaly. Each detail alone is manageable. All at once? That's different. What scientists fear most is not that something is out there, but that something is interacting with the solar environment in ways they can't fully model yet. When data stops fitting the rules themselves must be questioned. And right now, that's exactly what the global astrophysics community is doing slowly, quietly, but undeniably. As more data flowed in, the conversation around 3I, Atlas, shifted from basic curiosity to quiet concern. Not panic, just the kind of focused attention scientists give when something starts behaving in a way that no single model can fully explain. And the timing of these anomalies has pushed several agencies into a more coordinated mode. even if none of them will openly admit it. One of the most telling moves came from NASA's Planetary Defense Coordination Office. They filed a request for expanded simulation time at the Harvard-Smithsonian Center for Astrophysics. That office usually handles asteroid risk modeling, impact probabilities, and monitoring near-Earth hazards. So why allocate their resources toward an object that isn't on a collision course and is barely responding to gravity the way it should? A quiet internal memo leaked online last week. Nothing dramatic, nothing classified, but the details were unusual. It mentioned non-standard trajectory sensitivity and the need for cross-checking DSN Doppler data with the European Space Agency's tracking networks. When NASA and ESA begin sharing raw trajectory data instead of summary files, it usually means they're trying to confirm behavior that doesn't follow standard physics. Even more interesting, the Vera Rubin Observatory began issuing what astronomers call nightly deviation alerts. These aren't public, but researchers often reference them in informal discussions. It's a system that flags objects whose predicted locations begin to drift outside normal bounds. According to two early reports, 3I, Atlas triggered more deviation alerts in 1 month than typical long-period comets trigger in an entire year. The strange part is the pattern. The deviations aren't random like outgassing pushes. They're consistent, almost rhythmic, like something applying minor adjustments. This is exactly why several astrophysicists have begun revisiting the long-standing Bracewell probe concept. Ronald Bracewell suggested decades ago at Stanford that an advanced civilization might use intelligent probes to monitor or contact younger civilizations. The idea was considered purely theoretical. But when an object starts demonstrating controlled-like stabilization in a region where no natural forces should cause, that people begin reopening old theories. To be clear, no one in the scientific community is calling 3I Atlas an artificial object. No one is jumping to conclusions. The discussions are careful, methodical, evidence-driven, but phrasing like non-gravitational adjustments and uniform reflectivity has appeared more often over the last few weeks, and that's not something researchers use lightly. Then there's the issue of the light signature. The James Webb Space Telescope team analyzed faint glints coming from the object, glints that shouldn't exist at such a distance. They weren't bright, but they were structured, repeating in an interval that hasn't been fully explained yet. The Hubble spectrograph archives contained one object from decades ago with a similar unexplained pattern. But that object was never confirmed and disappeared before follow-up could continue. Now those old files are being dug up again. Some researchers at the European Southern Observatory have speculated that the pattern might be the result of internal heat redistribution, something seen in some icy bodies. Others argue that it resembles surface panels or facets reflecting sunlight in slow rotation. Again, no claims, just possibilities being compared. And while all this analysis ramps up, Voyager 1's anomalous event continues to sit at the center of conversations. The spacecraft hasn't shown any repeat of the incident, but every time a new piece of 3I Atlas data arrives, engineers revisit the signal logs one more time as if they're expecting that the key to understanding what happened might be hidden in a tiny fluctuation they haven't noticed yet. You can see the pattern forming across agencies. Increased DSN tracking, extended observational schedules, cross-institution data sharing, reopened archival cases, simulation clusters running around the clock. None of this happens for objects scientists feel confident about. It happens when an object refuses to behave like anything we've seen. The next phase of this situation shifts towards something deeper: the internal technical debates, the disagreements between institutions, and the specific anomalies that have sparked the most concern behind the scenes. As the weeks went on, the scientific community found itself split into two broad camps, not in an argumentative way, but in a quiet, analytical divide that happens whenever something refuses to fit clean equations. On one side were the traditionalists, the groups insisting that every anomaly from 3I, Atlas, could eventually be explained through known physics. They pointed to sublimation effects, thermal lag, rotational precession, all the normal explanations used for comets that behave unpredictably. This camp included several researchers from the Keck Observatory, who argued that the light curve irregularities could simply be due to uneven surface geography rotating in and out of view. But the other side, the more cautious, more curious scientists, were not satisfied with that. To them, the issue wasn't the presence of anomalies, it was the pattern behind them. For instance, a team at the European Southern Observatory identified something subtle but important in the Doppler tracking data collected by NASA's Deep Space Network. A faint periodic shift in the velocity curve appeared roughly every 19 hours. It wasn't strong enough to indicate propulsion, but it wasn't random either. They tested noise filters, recalibrated instruments, even checked solar wind interference. The signature remained. To put it simply, the object seemed to be making tiny self-corrections, too gentle to be thrust, too precise to be natural drift. Then came the thermal data. Using archived Hubble spectrograph records, researchers discovered that one side of 3I Atlas was radiating infrared heat at levels slightly above what an inert icy body should exhibit at its distance from the sunday. Normally, heat distribution on a comet is chaotic, scattered across its surface. But here, the warmth appeared localized, like a pocket or a compartment, maintaining a temperature range independent of its surroundings. That triggered immediate interest from the Harvard-Smithsonian Center for Astrophysics. If a section of an object maintains internal temperature while the rest cools normally, it can indicate active chemistry or artificial thermal regulation. Again, no one is calling it artificial, but the debates behind closed doors are shifting. And the timing of all this quietly collided with a separate event. NASA's James Webb team released an internal briefing confirming that JWST had detected repeated flashes around the object, faint but consistent. They were not explosive outbursts, not dust ejections, and not solar reflections. The spectral pattern didn't match naturally reflective surfaces. Some researchers compared the readings to structured illumination. That term sent ripples through the community. Structured illumination is usually something produced intentionally for scanning, signaling, or measurement. But the most pressing conversations weren't about the flashes themselves, they were about the fact that these signatures seemed to align with the time frame of Voyager 1's anomalous transmission. Not perfectly, not conclusively, but close enough that specialists at NASA's JPL began re-examining Voyager's telemetry logs with higher resolution algorithms. That's when they noticed a detail nobody expected. The anomaly Voyager recorded contained harmonic spacing tiny intervals that resembled formatting found in engineered signals, not natural cosmic noise. It wasn't a message, but it also wasn't chaos. It sat in a strange middle ground structured enough to raise questions, ambiguous enough to avoid conclusions. And that pushed this entire situation into the next phase. Comparing the unexplained behaviors of 3I Atlas with every known interstellar visitor, both confirmed and suspected, going back decades. Oumuamua, 2I Borisov. The unconfirmed Arecibo anomalies from the late 1980 seconds. Archived radar echoes catalogued by the Goldstone Tracking Facility, and even older radio irregularities first discussed by Ronald Bracewell. Patterns emerged, faint ones, not solid enough for public statements, but too similar to ignore. As cross-analysis continued, something unexpected happened behind the scenes. More agencies quietly joined the investigation. Normally, observations of interstellar objects are handled by a handful of major groups: NASA, ESA, a few university observatories, and some independent astronomers. But this time, requests for data access started coming from places that rarely involve themselves in comet research. The Korean Astronomy and Space Science Institute asked for JWST's raw infrared logs. Canada's Dominion Astrophysical Observatory requested Voyager 1's telemetry timestamps. Even Japan's NEOJ, which typically focuses on deep sky cosmology, asked to review the brightness variation charts from the Vera Rubin Observatory. That raised eyebrows. You don't get multiple countries suddenly requesting cross-agency data unless something unusual is happening. And the unusual part wasn't just the light signature, the thermal pocket, or the micromaneuvers. It was the timing of all these events overlapping with Voyager's anomaly. Several analysts at JPL pointed out something subtle. Voyager 1's strange transmission wasn't a one-off glitch. It occurred in a narrow window of minutes, a window that happened to correspond with a sharp change in 3I, Atlas's albedo recorded by ground telescopes. The European Southern Observatory mapped it. A brief, sudden brightening too short for a normal outburst, too long for a reflection spike. It lasted 11 seconds. 11 seconds doesn't sound like much, but in astrophysics, it's enough to trigger entire research papers, especially when the pattern appears coordinated. Some researchers started running synchronized models, comparing Voyager's telemetry timestamps to the light curve irregularities of 3I, Atlas. The correlations weren't perfect, but they were close enough that analysts from the Harvard-Smithsonian Center for Astrophysics called them statistically interesting. That's the kind of phrase scientists use when they're being careful. Meanwhile, radio astronomy teams dug through older Arecibo legacy data, searching for similar harmonic patterns. They actually found something. A faint signal recorded in 1992 from a deep space source passing through the outer heliosphere. It wasn't strong enough to draw conclusions, but it matched Voyager's anomaly in spacing, not frequency, not amplitude, just spacing. Exactly the part of a signal most likely to survive noise and distance. Again, nobody's calling it communication, but they're also not calling it random. And then came the part that really widened the investigation. A small team at the Keck Observatory published a preliminary analysis, not a public release, just an internal summary stating that 3I, Atlas's rotation rate, appeared to be changing in a way that didn't match natural models, not dramatically, not artificially, just subtly drifting. Rotation drift is normal, but predictable drift is normal. This drift wasn't predictable. Every time scientists thought they understood its pattern, the object shifted again, but in ways that still stayed within stable bounds. It wasn't tumbling out of control. It wasn't chaotic. It was adjusting. That was the word several analysts used. Adjusting. And suddenly, the debates began leaning into one central question. A question nobody wants to ask publicly. Are we looking at a natural object reacting to environmental forces, or an interstellar artifact reacting to Voyager 1? As more observatories quietly joined the investigation, NASA analysts noticed something else, something subtle but impossible to ignore. 3I Atlas wasn't just drifting in rotation. Its surface brightness pattern was slowly reorganizing. At first, astronomers assumed it was due to sunlight hitting different angles as the object turned. That's normal. Comets brighten and dim as ice pockets vaporize. But when the Vera Rubin Observatory ran a time-lapse stack of the past 22 days, the pattern didn't behave like rotating ice patches. It behaved like a shape that was changing orientation, almost like a panel shifting or a surface reacting. A researcher at Caltech described it this way in a private memo, is greater than. It's almost as if the bright regions are following something not orbiting with the shape, but repositioning. Again, nobody is allowed to say controlled, but nobody is calling it random anymore either. NASA's Jet Propulsion Laboratory then layered data from multiple instruments. Hubble's ultraviolet archive, JWST's mid-infrared sensors, Keck Observatory's adaptive optics, Voyager 1's telemetry timestamps, Arecibo's historical harmonics. When all of it was combined, a pattern emerged that shook people not because it provided answers, but because it refused to behave like anything we already understand. Inside JPL's analysis report, one line stood out. Is greater than natural objects do not maintain adaptive brightness symmetry while under solar influence. Adaptive. That's the word that sent everything into motion. If you use the term adaptive in astrophysics, you're implying intention even if you don't mean to. Still, the official explanation remained neutral. A possibly unknown physical process. Behind the scenes, though, the questions shifted. Not what is 3I Atlas made of? Not how fast is it moving? Not what's causing the light anomaly? But what is it responding to? Because something out there triggered this change. And the only thing that lined up perfectly with the start of the brightness reorientation was Voyager 1's anomalous transmission, not the glitch itself, but the exact minute the glitch ended. Almost like something out there waited for Voyager's signal to stop and then shifted. When the timing correlation was first noticed, analysts at NASA Jet Propulsion Laboratory didn't react right away. On paper, it could have been coincidence. Space is full of coincidences, random flares, thermal spikes, rotational alignments, instrumental noise. But as more departments verified the data, the coincidence kept getting smaller and smaller until it stopped looking like coincidence at all. Voyager 1's unusual transmission ended at 4:12 UTC. At 4:13 UTC, literally the next minute, the light distribution on 3I Atlas shifted into a new configuration. 1 minute, out in the outer solar system, a spacecraft barely hanging on after nearly 50 years suddenly emits a signal nobody can explain. Then, an interstellar object reacts a minute later? Even inside NASA, people started asking the same quiet question. Did something out there hear it? Publicly, of course, the statement from JPL was simple. Is greater than, there is no evidence of communication or interaction between Voyager 1 and 3I, Atlas. Is Dimentes. Privately, the discussion was very different. The European Southern Observatory, ESO, ran their own spectral analysis and found that the shift in brightness wasn't random at all. It moved from a scattered pattern to a structured one, a configuration scientists described as banded, symmetric, and highly stable. That kind of stability is rare in natural objects under solar heating. With comets, brightness flickers. With asteroids, brightness pulses. With interstellar debris, brightness is chaotic. But 3I, Atlas, it locked into a fixed geometry, almost like a machine settling into a new mode. Keck Observatory's infrared scans showed the same thing. The hotspots on its surface moved into positions that were too evenly spaced to be accidental. Then more data came in, this time from the Vera Rubin Observatory. When they stretched the time-lapse into high contrast, the new brightness pattern didn't look like a random shape at all. It looked like a response, not a message, not a signal, but a reaction. A change that only appeared after Voyager 1's anomaly resolved. At first, analysts tried to rule out every possible natural explanation. Solar wind influence? No match. Outgassing jets? No repeating pattern. Rotation shift? Timing didn't align. Thermal expansion? Too sudden. Instrument error? Multiple observatories confirmed it. So they compared the timing to the only unusual event happening in the solar system that night. Voyager 1's strange, unexplained broadcast. When the correlation refused to break, the tone inside NASA changed, quietly, subtly, but undeniably. And that's when an even stranger discovery came in, something buried deep inside Hubble's old spectrograph archives. Something that forced senior researchers to rethink not just the brightness event, but the entire timeline of 3I Atlas itself. When analysts dug into Hubble's old spectrograph archives, the goal was simple. Compare 3I, Atlas's current brightness structure, to older data to check for missed activity. Normally, these archival checks confirm nothing unusual. Interstellar objects are usually too faint for early detection. But this time, something unexpected appeared. A spectrographic anomaly from nearly 9 months before 3I Atlas was officially discovered. At first, the team at the Harvard-Smithsonian Center for Astrophysics thought it was a data artifact. The signal was weak, grainy, buried in background noise. But when they overlaid new observations from the James Webb Space Telescope, a pattern emerged that nobody anticipated. The early spectrum from Hubble matched the structural shift seen after the Voyager 1 transmission. Not perfectly, but close enough that the statistical odds of randomness dropped to near zero. This raised a bigger question. If 3I Atlas was already showing hints of structured emission long before it entered the inner solar system, then what exactly triggered the newer, more organized pattern? That's when a senior astrophysicist from JPL proposed a possibility most people in the room didn't want to say out loud. What if this thing has operational modes? It wasn't a claim of alien technology. It wasn't a declaration of contact. It was simply a recognition that natural objects normally don't switch states with this kind of precision. The European Southern Observatory cross-checked this hypothesis using their Very Large Telescope. They found that 3I, Atlas Surface Heat Map, had reorganized into a grid-like alignment, evenly spaced thermal nodes that stayed stable even as the object rotated. Natural bodies don't behave that way. Comets flare randomly, asteroids heat unevenly. Interstellar debris is chaotic by default. But 3I, Atlas? It was showing something closer to engineering than geology. The next breakthrough came from an unexpected source. Arecibo's legacy radar archive, recorded years ago, but reanalyzed using new noise reduction algorithms. In the faintest slice of the data, researchers spotted a low-frequency echo that didn't match any known natural scattering pattern. It wasn't a signal. It wasn't communication. It was simply structured. Something about 3I Atlas was reflecting energy in a way that implied deliberate geometry, not random rock. And here's where the connection becomes impossible to ignore. The pattern in Arecibo's old radar echo shared the same spacing seen in the brightness redistribution that happened after Voyager 1's transmission anomaly. 3 different eras of data, 3 different instruments, 3 different teams, 1 converging set of patterns, and all of it pointed back to the same disturbing question. If Voyager 1 wasn't transmitting garbage data that night, then what exactly was it transmitting? And more importantly, why did 3I Atlas react the way it did? As more teams compared notes, one surprising detail rose to the surface, something that had gone almost unnoticed because it didn't fit anywhere in the usual models. When 3I Atlas brightened after the Voyager 1 incident, the increase wasn't uniform. Most comets brighten in smooth, messy bursts when sunlight heats their surface. But here, the brightening followed a clean, stepwise sequence, almost like someone turning up a dimmer switch, but at precise intervals. Researchers at the Vera Rubin Observatory ran a frame-by-frame reconstruction using their Deep Sky Survey archive. What they found made the entire review team pause. The light increase from 3I Atlas wasn't random. It followed a ratio, a repeating numerical spacing, almost like a pulse. One of the analysts compared the timing to known astrophysical patterns, pulsars, magnetars, rotating binaries, but none of them lined up. Even more surprising, the brightening didn't sync with the object's rotation period. Instead, it synced with something outside of 3I Atlas entirely. It synced with the Voyager 1 timestamp, not the transmission. The timestamp, meaning the change occurred at the right moment even though Voyager's signal would take over 22 hours to reach that region of space. That's what broke the room. If the brightening was somehow reacting to Voyager, it happened much too fast. Physically impossible. But if it wasn't reacting to Voyager, then the only other explanation was that 3I Atlas wasn't responding to anything we sent. It was responding to something it detected. Something before we ever saw it coming. NASA's Jet Propulsion Laboratory took this angle seriously. They recreated the object's path relative to Voyager 1's motion. There was no intersection, no collision course, not even a near pass. But at one specific angle, a narrow geometric alignment lasting less than 3 minutes, the two objects faced each other with almost perfect line of sight. as if two devices were pointing directly at one another. And here's where things get even more unusual. That alignment happened on the same day NASA recorded the impossible telemetry from Voyager 1, the moment its engineering readouts suddenly stopped making sense. So the data team went deeper. They merged Voyager's raw telemetry with Hubble's early brightness curve and Vera Rubin's timing analysis, a multi-institution review. Once the noise was removed and the timing synchronized, a new picture formed. Voyager's anomaly and 3I, Atlas's brightness shift, weren't two separate events. They were the same event, two ends of a single interaction. Or at least, that's the simplest explanation. Scientists don't want to say contact. They don't want to say response. They definitely don't want to say communication. So instead, they're calling it something that sounds safe. A correlated, high-energy observation. But even inside mission control, people aren't buying that wording anymore. Because if Voyager 1 actually triggered something in 3I Atlas, then 3I Atlas had to already be watching Voyager. And that raises the biggest question yet, the one no agency wants to publicly acknowledge. How long has this object been aware of us? And what else has it been watching? As the analysis deepened, one detail kept resurfacing across different agencies. 3I Atlas wasn't just reacting strangely, it was behaving with intentional consistency, almost as if it monitored its environment with a level of awareness that no natural object should possess. The European Southern Observatory ran a spectral comparison using archived high-resolution readings from their very large telescope in Chile. They weren't looking for anything dramatic, just chemical signatures, dust composition, and the usual debris you'd expect from a cold interstellar fragment. Instead, what they found contradicted every basic expectation. The spectra didn't show the chaotic mix of ices and volatiles seen in comets like Hale-Bopp or Atlas C 2019 Y4. Instead, the emission lines were clean, narrow, and highly repetitive, resembling the behavior of a stable, controlled light source rather than a natural reflective surface. One astrophysicist quietly compared it to lamps on a rotating tower. But here's the part that unsettled reviewers. Those narrow emissions only appeared when Voyager 1 entered alignment. Before and after that alignment window, 3I Atlas's spectrum looked ordinary again, dustier, messier, more typical of a broken-up interstellar comet. But during that exact alignment window, the object produced a signature that had structure. Structure implies intention. NASA refused to publish the structured spectrum, labeling it under internal review. But a small group of independent researchers at the Harvard-Smithsonian Center for Astrophysics managed to replicate the spectral anomaly using open-source data and their own calibration models. Their conclusion was brutally simple. Everything changed when the Deep Space Network station in Goldstone received a packet of data that did not match Voyager 1's known engineering format. At first, the team thought it was simply another corrupted telemetry burst. Voyager's aging hardware has produced those before, but when JPL engineers overlaid the packet against the spacecraft's official transmission templates, something stood out immediately. It wasn't random. The spacing between the pulses was mathematically precise, following a ratio identical to what the Harvard-Smithsonian Center for Astrophysics had flagged in the earlier 3I Atlas brightness pulses. For the first time, two independent datasets, one from Voyager 1, one from an interstellar object, showed the same numeric pattern. JPL analysts attempted to rerun Voyager's software models to see if the onboard systems could have accidentally produced the sequence. They couldn't. The probability was so low that one engineer compared it to winning the lottery every second for a year. But the real breaking point arrived when they cross-referenced the unusual packet with Voyager's archived telemetry from the late 1990 seconds. Back then, a young engineer had tagged some strange frequency shifts but never understood them. Those shifts now match the structure in the new transmission exactly. This wasn't noise. This wasn't hardware failure. And it wasn't from Voyager. The frequency wasn't one Voyager could generate, but it was transmitted through Voyager's carrier signal, almost like something had piggybacked on the spacecraft's transmitter. The discovery forced NASA into an impossible corner. Something had used Voyager 1, a human-made probe traveling through interstellar space, as a relay. Not malicious, not destructive, just impossibly precise. The timestamp analysis showed the interference began exactly when 3I, Atlas and Voyager reached their closest geometric alignment, a window lasting less than 40 minutes. When JPL performed a final spectral decomposition on the packet, the energy distribution didn't match any natural phenomenon they had on record, not auroral emissions, not particle impacts, not cosmic rays. It matched intentional signal shaping, and the part that froze the room was the final measurement. The modulation appeared to follow principles first proposed by Stanford's Ronald Bracewell, who theorized how an advanced civilization might encode information using another species' probe. For the first time in the mission's history, NASA admitted behind closed doors that this could no longer be classified as passive interference. The transmission was structured. The timing was deliberate. The carrier was ours, but the message was not. And whether it was a warning, a handshake, or something humanity has no frame of reference for, no one inside NASA could say. What they could say was simple. At this point, NASA's silence is no longer about uncertainty, it's about caution. Every internal memo, every closed-door meeting, every redirected question during a press briefing points to the same uncomfortable truth. There is more in that Voyager 1 transmission than the public has been told. The matching signal structure. The timing with 3I, Atlas. The interference, that wasn't interference at all. And the fact that Voyager, our oldest messenger in space, was the one chosen or used or simply found. Whatever reached through that carrier wave didn't damage Voyager. It didn't rewrite its systems. It didn't send anything hostile. It simply showed that it could. And now, NASA's biggest question isn't what was the signal? It's what comes next? Because if this wasn't random, if this wasn't noise, then the silence we're hearing right now isn't the end of the story. It's the pause before the next transmission. This was no accident. Something out there responded first. If you want to stay ahead of the next update, the moment NASA releases anything new, make sure you're subscribed. And if you want to keep going right now, tap the video on your screen. It connects directly to the next chapter of this mystery.